Okay, this problem was posted several years ago. One of my students stumbled upon it and asked if I could help out with some of the steps, so I'm doing the complete solution. This function f of x is a rational function, and if you use a forward slash to separate the numerator and the denominator, you really should put the denominator in parentheses. If you can use a horizontal bar called a vinculum to separate the numerator and denominator, then you don't need grouping symbols. So there's the function we're trying to answer these questions about. It is symmetric about the y-axis because it's an even function, like f of 3 equals 9 over 9 minus 4 or 5, and f of negative 3 gives you the same value. In other words, opposite values of x give you the same y value. So the function is even and symmetric about the y-axis. For the rest of these, we're not going to answer them in the order given here. We're going to kind of draw a rough sketch using these guidelines, which don't include any calculus at all. To find the x-intercepts, we want to know what values of x make y equal to 0, and that only happens when the numerator is 0. So for our problem, when does the numerator equal 0? When x squared equals 0 or x equals 0, when x equals 0. Of course, we found out that y equals 0, so there we plotted the x-intercept at 0, 0. That's the only place the graph crosses the x-axis. Find the real zeros of the denominator, h of x. That will tell us where the vertical asymptotes are, and that tells us where the function is not defined. It helps us determine the domain. So if x squared minus 4 equals 0, x squared equals 4, applying the square root property, x equals plus or minus 2. So that's these two red dashed lines. And the graph of a function can never cross any of its vertical asymptotes. So we know we're going to have three branches for this curve. Left of the red line, between the red lines, and to the right of the red dashed line on the right. Okay. Find the y-intercept if it exists. That means put 0 in for x. Well, we've already seen that 0, 0. Apply the theorem on horizontal asymptotes. What is that theorem? Well, I don't have it written here, but what we do is examine the coefficients of the highest degree terms of the numerator and the denominator. If the highest degree of the numerator equals the highest degree of the denominator, then the coefficients of those terms forming a fraction like this give us the horizontal asymptote, and that's y equals 1. So that's this green dashed line right here. If there is a horizontal asymptote, and there is, determine whether it intersects the graph. Some textbooks call that find the crossing points. I haven't seen that in too many textbooks, but every now and then. So we want to know, does the original function ever equal 1? And if we solve that equation for x, we get 0 equals negative 4. So no, there are no crossing points. The branches of this curve never cross this green dashed line. So now we can kind of draw a rough sketch without any calculus at all. If we find f of 1, that's negative 1 third. That's to the right of the dashed line. So the curve has to go through that point. What did I do here? F of 1. Oh, here's f of 1 right here. Okay, there's the negative 1/3 right there. I was thinking that was the one. So and so the curve can never cross this green dashed line, but we don't really know if it turns around at 0, 0 or not. It could maybe turn around up here. So that's where the calculus comes into play. And then for a branch to the left of this red dashed line, I found f of -3. And as a graph approaches its vertical asymptote, it either goes to positive infinity or negative infinity. And it has to cross it or approach its horizontal asymptote. So you can draw a rough sketch just by finding this point right here. And the same for this one. F of 3 is 1 1/5. Can't cross the green dashed line, so it has to approach its horizontal asymptote from above, and its vertical asymptote, it's got to go to positive infinity. Can't go to negative infinity because it can't cross the green dashed line. Okay, so there's a rough sketch. Now let's use some calculus. So here's f of x. Here's application of the quotient rule, the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Now, instead of multiplying this stuff all out together, this is what frequently happens. On both sides of this minus sign, there's a common factor of 2x. So if you factor out that 2x now, you'll make your work a lot easier. So what's left if I pull out this 2x? From the first term, we get an x squared minus 4, and from the second term, a minus x squared. These combined is 0. Negative 4 times 8x is negative 8x. So there's your first derivative. And to find the critical numbers, we want to know, when does that equal 0? Well, that equals 0 when the numerator is 0, which is 0. And also when the denominator is undefined. Well, those are our vertical asymptotes. So when you do your little number line here, or sign graph, my suggestion is to put x's where there are vertical asymptotes. So you're picturing there's a vertical asymptote here. So there's no point on the curve at those points. And then find out what's happening to f prime in each of those intervals. And of course, we have the critical number 0 here. So f prime of -3 is positive. So the tangent lines have a positive slope. So the original function is increasing. The same between -2 and 0, increasing. To the right of 0, decreasing. To the right of 2, still decreasing. So right here, since the function went from increasing to decreasing, we have a relative maximum. Okay, and if we go back to look at this rough sketch, we can see increasing to the left of -2, decreasing to the right of -2, increasing to the left of 0, decreasing to the right of 0. Okay, so our calculus matches. And we can see that this guess for the relative max was correct. As far as the second derivative, here's the first derivative. Apply the quotient rule again. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. That's what all this is. Power rule, followed by the chain rule. And then notice that every term contains a factor of -8 right here and a factor of x squared minus 4. So if I pull out a -8 and an x squared minus 4 from this first term to the left of this minus sign, there'll only be an x squared minus 4. To the right of the minus sign, I pulled out a -8. I pulled out this x squared minus 4. What's left? 4x squared. And of course, this minus sign. So that becomes, oh, by the way, now one of these x squared minus 4s cancel out. So I've got -8 times -3x squared minus 4. If I distribute the -8, there's your second derivative. And some observations about that: it can never equal 0 because this numerator can never equal 0. It's always got to be 32 or greater. And the numerator is never negative. So when we draw a little sign chart, we don't have any critical number or hypercritical numbers. as some textbooks call them. But we do have branches that we can talk about the concavity. Okay, so f double prime to the left of -2 is positive. So concave upward, think smiley face for positive. Negative between -2 and 2, so concave downward, and to the right, concave up. Okay, and that matches our little sketch right here. Concave up, concave down, concave up. If I go to board 5, there's a graph from Desmos. Vertical asymptotes never crossed. Horizontal asymptote is never crossed. 0, 0 is a relative max. And this table right here shows you what's happening as x approaches negative infinity. We're really close to 1. We'll get closer and closer from above, but never hit that horizontal asymptote. And then these numbers right here show you what's happening as we get close to the left vertical asymptote. We're approaching positive infinity. At 0, we have that relative maximum. And then to the right of this vertical asymptote, to the left of this vertical asymptote, we're approaching negative infinity. We get to the right of it, we're approaching positive infinity. Okay, there you go. Hope that helped. If you have any questions, post a comment.